All right, everybody. So here is the lecture on food web properties. So there's all sorts of ways that we can characterize food webs. We can look at, how connected food webs are, the fraction of top predators, the fraction of basal species, the maximum trophic level, how much omnivory there is, how much cannibalism there is, all sorts of different ways that we can think about different species or different food webs, and so I want to go over a couple of the most commonly used food web properties. So the first one we're going to talk about is food web connectance. Now, connectance, what it is it is looking at right here how many of the possible links in a food web are actually present. Okay. So, and it's used by this equation. So basically, how connected the species in the food web are to each other compared to a maximally connected food web where everything is connected. So maybe write this out a little bit more easily understandable. So what this is looking at is the L is the number of links present in your food web. And then this portion right here is the maximum number of links possible. Now these are meaning, just undirected one-way links, or we're just saying species A is connected to species B in some way. Like species A could eat species B, or species B could eat species A. We're not really saying that here in this case. So if you do this, you can see that all food webs, basically everything doesn't eat everything else in a food web, right? So we know that from, say, a whale shark here, right? It's eating a bunch of tiny little fishes, and what's happening is, whale sharks are really great at eating small things, but they can't eat everything, right? They can't, even though they themselves are quite large animals, biggest fish in the world, right? They're not going to be able to eat anything. The size of their throat is like as big as your fist. So, they can't eat very big things. So what we see is, varying levels of connectance have to do with prey size constraints. Basically, how big is your mouth, and what type of mouth that you have, and which can eat different things. And then there might just be feeding preferences of different organisms. This is one of my favorite gifts here, where we've got this, I don't even know what fish this is, but eating this dogfish, right? But this type of feeding method here is great for eating large fish, but it's not going to be, it's a lot of energy wasted if it's going over a tiny little fish. So what we see is with connectance, let's explore that a little bit here, where we've got a 3-species system, basically 2 predators and 1 prey. And when we do this equation out, what we see is that there are 2 links here. Basically, species B eats species C, and species A eats species C. Right? So you put that 2 in that links, and then there's 3 total species. 3 times 3 minus 1 over 2. And what you eventually get out of it is 2/3. And, this is obviously pretty easy to see that we have the only connection we're missing is that, like, species A eating species B or something like that, right? So we have 2 out of the 3 connected 2 out of the 3 species being connected here, giving us a connectance value of 2/3 or 66.7%, right? So let's bring it up to a little bit more complicated food web here, where we have 6 species, and what you can see here is species A is connected in some way to every single other species. Same with species B. Every single species is connected to every other species. And what you get with 6 species, you get 15 links. So that would be a maximally connected food web. Now this doesn't happen, right? Because if F here is a top predator, it can't eat necessarily So in this made-up example, this is unrealistic because the top predator probably is not going to be able to eat plants down here, right? Even though we have arrows going there, right? So what we see is, we don't get maximally connected food webs really ever. This is something that might be a little bit more realistic, where here we have 7 different arrows, links, so we get 7 over 15, 46.7% connected, and then, a less connected food web over here, where we get 0.33, okay? So, more connected, less connected food web. So what's the point, right? Why do we care about this connectance idea? Originally, connectance was just used as a descriptive property. It was basically just something that we could use to talk about 2 different food webs. But what it's really become recently is shown to be an emergent property, okay? And really this is based on optimal foraging. I kind of hinted at that earlier, but think about this shark here, right? This great white shark eating a seal. Why is it eating a seal? So let's say this is the great white shark here, species 4, and this might be a little bit more realistic, this food web. Great white shark eating the seal, which is species 3. The seal then eats 2 different species of fish or something. So think about the energy it takes and the morphology that is needed to chomp that seal, right? You need these super big mouth, big teeth, be able to swim fast to catch up to that seal, surprise it, whatever that shark needs. There's trade-offs there. So the shark is not going to be able to eat the tiny little fish that this seal is going to be eating itself, right? If it were to go after those fish, it would, use so much energy swimming after just a tiny little mouthful, and it probably, wouldn't get enough food from that. So we don't see these tiny fish connected to the great white shark because it's just not worth it. It's suboptimal foraging, right? So species, through their morphology, through their behavior, have optimal foraging strategies that then necessitate that the food web is less connected than, say, this here maximally connected food web. So it's a property that emerges based on realistic biology. So there's been a lot of research looking into how connected a food web is and its stability. And what we see as more simple communities, what we generally think of as less connected food webs, are really prone to fluctuation, right? So in the Arctic regions, we have a lot of examples of this, where there's simple communities that have, say, the classic fluctuations we see of snowshoe hare and lynx, of lemmings and snowy owls, where lemmings can have huge numbers of increases, and the population crashes, and the owls then can really respond to that. So but we oftentimes see in reality that these simple communities are really prone to fluctuation, and the question is, well, why is that? And we can look at that from a connected standpoint, and we can even just look at it for a portion of the food web. So think about species A and D here. We've got 2 species. D is getting 100% of its food from species A. And they're what we would call a strongly interacting species, right? So essentially, the abundance of species D is going to be really wholly dependent on species A. Now, there might be some other environmental factors that can impact it, like nesting sites or obviously the species F can affect D here, like via predation. But from just a food standpoint, there needs to be, if there isn't enough species A, there isn't going to be any species D, right? Because there's not going to be any food for them. So any fluctuation in species A will probably filter up very strongly and cause strong oscillations in the population of species D. And that's what we see kind of here going on, where the lynx is highly connected. The lynx is the red, right? Is highly connected to the abundance of the snowshoe hare. Well, but think about another situation where you have species E here. Where what we oftentimes, the logical argument is that large numbers of weak interactions can buffer and damp the oscillations of one species. And just think of it here, species E here, what's going to happen to species E if species B decreases or goes extinct? Now, potentially, it would lose half of its food, okay? But, in best case scenario, species E might just do just fine. It just starts eating more species C. So it can survive at least some oscillations in species B, and those, because these interactions are weaker than, this thicker one where 100% of the food of species D is species A, because they're weaker interactions, that species E can survive that extinction or those oscillations of its basal species. And so when we bring this out into a whole food web context, right, the more connected a food web is, the more species are predicted to be able to survive those oscillations, or the fluctuations in one species shouldn't impact that much the whole entire food web. The thing is, there's a lot of really conflicting results of this. So when we do simple models of food webs, we see that more diverse, more connected food webs are actually less stable. The thing is, a lot of that work is done with really simple food webs in comparison to what reality is. And I'm talking like 4 to 5 species, right? And really, there's very few food webs that only have 4 species. Models really show, these simple models show that more connected, more diverse food webs are less stable. All the logical arguments kind of go towards that there's more diverse, more connected food webs are more stable. And so it's really kind of confusing, and this is a really active area of research, and it's really context dependent. And I think it's really hard to make a generalization about food webs. Basically, every food web is really unique. Each ecosystem, even if you have the same players in a food web, the ecosystem might be similar or very, very different. A single species, the addition of a single species really can change the entire system. And then when you get back to this question of, how does complexity, how does connectance, how does diversity of a food web change its stability? What is a more complex food web? Now, generally you would expect the more species you have, yes, that would increase complexity. But does a more connected food web actually have, is that more complex, or is a less connected food web actually complex? So it's really, this idea of complexity and stability is a really active area of research, and it's a really very confusing and different ways to think about all of the issues that make it such an active area of research. And I would say that this is one of the things that we'll see in the next couple decades to really help us learn about how food webs actually work. So through reading the chapters, you might be interested of why do so many food web ecologists talk about food web stability? And that's a really good question, because from my viewpoint, I look at the ecology of temporary ecosystems, right? So where my aquatic temporary ephemeral wetlands, is for most of the year looks like this. There's no water there, right? and the playas then fill up with water and have a very short-lived hydroperiod. So when we're talking about stability in a context of here and how stable the food web, it just doesn't make sense, right? There is essentially no stability in the food web over time. But I think what it comes from is there's always been this people want to know about the balance of nature, right? And the balance of nature is really non-existent, right? The only consistent thing in nature is constant change, right? I've said that in a variety of different classes, but we've this idea of balance of nature kind of came out with that the ecological thinking about equilibrium processes and focusing on climax communities. But recently, more and more ecologists have focused on dynamic systems and seeing how how does the food web change, and really how does the dynamism of a ecosystem impact the stability of the food web. So I would say that in a lot of senses, focusing on this idea of stability is not necessarily important. However, if you're trying to figure out how to save the giant panda, but you're working in a system that is maybe really fluctuating a lot, if you're putting in a ton of money to try to save an endangered species, I understand why hopefully having that ecosystem be stable enough that the populations can rebound is somewhat important. So there is I don't want to just say stability is pointless, right? Like we shouldn't care about a stable food web. There are certain times where food web stability is extremely important. All right, with that, I'll see you later.